So let us talk a little bit about statistical methods. So what we assume here is that you have temperature measurements for a certain location over many years, okay, and you derive daily average temperatures. And then you work out how many days of your measurements are within certain temperature ranges. Say between 12 and 13 degrees, how many days do you have? Or 14 and 15 degrees Celsius, and so on. How many days do you have where the temperature is between 35 and 36 degrees Celsius? And then you sort your data in something we call it a histogram, okay? But it shows you a distribution of how many days you have within certain temperature intervals. Okay, and what you get, and what you often get, is something which we call a normal distribution. And this one is a very busy diagram, and we'll spend a little bit of time with it. But let's just assume you have your temperature distribution. Okay, and your temperature distribution looks like this. You get a symmetrical curve, okay, and this is theoretical, so in reality you get slightly different curve, but just assume that you have a symmetrical curve, and the most often observed value, okay, of your temperature actually refers to the mean value, which is shown here in the middle. Okay, and in this example is also the median value. And you can work out what that means. Okay. So you sorted all your data, and this one is the most often occurring value. Okay, and then temperatures which are higher or lower occur less often. This is why your curve, okay, decreases as you go to the right or to the left. Left means colder, right means warmer. Okay. And this frequency, or the number of days that you get, we call it the probability density, and we can express it in percentages, okay, in relative to the total number of, and we call it events. So each day in this case, we call an event. Okay? So you get that distribution. You can work out what the mean value is. Okay? But you can also work out something that we call the standard deviation. Okay? And the standard deviation tells you about the spread of this curve. Okay? Whether you have a very narrow bell-shaped curve or whether you have a very wide bell-shaped curve. Okay, and so this is the next thing this is shown in this graph, is here on this axis. In terms of standard deviation, it tells you where do you have plus 1 standard deviation or 2 standard deviations or 3 standard deviations, just as reference points. Also, where do you have minus 1 standard deviation, minus 2, minus 3, or minus 4. Okay, and the standard deviation is something you can calculate. So you plug in all your values and you can work out what is this sigma symbol here. So it stands for a specific number. Okay? And then you can relate these numbers or the intervals that you get with percentages. For example, if you just look at the range, which is defined by mean value minus 1 standard deviation, which is here, and mean value plus 1 standard deviation. So you're talking about this part of your distribution, okay? And you can work out that the number of days within this range amounts to 68% of all values are within this range. Okay? And that's, if you have this normal distribution, that's the case for any normal distribution that you get. Okay? So higher temperatures outside this range, either warmer or colder, occur less often. Okay? So let's have a look at the extreme ends of this distribution. If you look at, there is something, 3 sigma, 3 standard deviations, and let's have a look at these cumulative percentage, what that means. So if you start on the left side, you look at the very coldest days, then there's only 0.1% of all events. Okay. 0.1% are below mean value minus 3 standard deviations. Okay. And this is what we call extreme events, because it refers to 1 in 1,000 events. So if you have 1,000 events, only one of them is statistically in this range of very cold temperatures. Similarly, if you go to the other end, and this is cumulative, if you look at all events, if you sum up all the events, 99.9% are within mean value plus 3 standard deviations, and anything higher of higher temperatures in your example, okay, only occurs 1 in 1,000 days in this example. Okay? And this is what we call percentiles. So often extreme events are defined by 1% or 99% percentiles. Okay, so does that make sense? All right. Okay. Yep. So, next thought is, well, how can you now check whether an extreme events or the occurrence or the frequency of extreme events has changed? Okay. And what you do is you exactly use these distributions, and you do it for a reference time period, say 30 years ago, and then you compare it with how it is today, okay, or how it is currently, and you can compare. And there are different ways that these curves can change. Okay, and this one is an example that only looks at hot and cold weather events. So again, we look at temperatures, but indeed you can construct these curves for other type of variables. So just have a look at the first example, which is shown on the left side. Okay, so you have your reference distribution, which is the solid black line. Okay, and you can define what are your extreme events. Okay, so now if you assume that there is a warming during the entire seasons, during the entire time scale, so the entire curve shifts to the right, and this is the dashed curves. Just assume that this happens. You have a warming throughout, influencing the cold and the warm season. What this implies is that you get more hot and extreme hot weather events because you shift this distribution to higher temperatures, and you have less cold and less extreme cold weather events. Okay, well, that makes sense, doesn't it? Okay. There's another possibility. Another possibility is actually that your distribution changes in terms of an increased variability, that you also get more extreme cold weather and more cold weather. Okay, and you already guessed right that the extreme cold weather is defined in terms of 4 standard deviations, and the more cold weather is here the part, it's between 3 and 4 standard deviations. So you can actually look at different subdivisions. Okay. What also can happen is that the shape of the distribution changes, which is shown here above my head. So the black curve is the reference, and you actually get, in this example, no change in the extreme cold or cold weather events, but you get more extreme hot weather events. Okay, so these distributions are extremely helpful in order to understand changes, and also, in particular, not only of the mean, but also of the number of extreme events. Okay, so this is what scientists use. All right, so what do we do next? Let's see what happens, okay? All right, okay, so here we go. So you think about it and do some brainstorming, and you think about what can you actually use as an index for temperature or for extreme temperatures. Okay, so you have daily data. Okay, that's the basis, daily data, and you can do an event analysis. And an event analysis means counting the number of days that satisfy a specific condition. And then you can look at do a trend analysis. You can compare. Did this number increase or decrease? Okay, and this is from the Bureau of Meteorology, and that's the extreme temperature indices that they use. So that you just get an idea of that it's not only one index. So it's a wide range. Okay, so for example, okay, very hot days are defined as the annual count of days with maximum temperatures exceeding 40 degrees Celsius or 35 degrees Celsius. Okay? And these are absolutely robust definitions. You just count the days, and then you can see whether this number increases or decreases. Okay? Very hot nights and hot nights. So it's about the nights with minimum temperatures above a certain range. You can do the same thing for cold nights, cold days, or very cold days, very cold nights, frost nights. Frost nights where the temperature is below 0 degrees Celsius. Okay? Warm days in general, and you can look at, this is defined in percentage of days exceeding the 90th percentile. This is based on 90%. Okay? And warm nights, similarly cool nights, cool days, here you have the 10th percentile or 10%. Okay? Then you can look at the highest maximum temperature. Okay. Highest minimum temperature, and so, you can warm spell duration. You can actually count the number of days with at least 4 consecutive days when daily maximum temperatures exceed the 90th percentile, the 90% value. Okay, cold spell duration, growing season length. You can also look at seasons, okay, based on temperature thresholds. So for each of these indices, you can do statistics and counting days and look at changes. And that's what the Bureau of Meteorology does. You can also do something similar based on rainfall. Okay, rainfall is the other important parameter, climate parameter. Let's have a look how that looks like. Okay, that's what the Bureau of Meteorology uses, but it's used by worldwide by other agencies. Sometimes the definitions are a little bit different, but that's the same principle is used worldwide. Okay. For example, wet days. Wet days are defined as an annual count of days with daily precipitation exceeding 1 millimeter. Okay. Heavy precipitation days, annual count of days with daily precipitation exceeding 10 millimeters. Very heavy, 30 millimeters. Okay. And some other very wet day precipitation, extreme wet day, you can go through all that day. Consecutive dry days, consecutive wet days. Okay, so how many days in a row did you have precipitation less than 1 millimeter? Or exceeding 1 millimeter? On the basis of that, you can do the statistics. So that's really the key to understand how scientists work out changes in extreme events. Okay. And this concludes the second part of this lecture.